Hello everyone, my name is Maxime Chagnot. I'm a CATIA consultant working for PLM Technology in Norway. And today I'm going to perform a live demonstration of the 3DExperience release 19x on cloud. And the topic of this video today is to show you a great application called Functional Generative Design. That is basically topology optimization for 3D parts and also the preparation for manufacturing and 3D printing. So let's see how it works. It's very simple. I have this 3D part already created. While it's brackets, 10 millimeter thickness, 150 millimeter and 75 millimeter this direction. And we have a material already applied. It's aluminium, and it's very important for you to apply it on the 3D part level and not the 3D shape. Okay, so the first thing we will do is make a copy of this part directly inside, or copy of the shape directly inside the 3D part. And for doing so, if you have seen already some of my videos, we can just create an abstraction shape. So you see, insert, here it is. You can even change the name. Let's call it new gen shape for new generation. And we will copy this part body, so copy here, and you will paste it with a special attribute as result with link, because you want, if this part is modified, you want your design to be following this part. We will hide this part body because we don't use it, and of course both of the parts are overlapping right now, so we'll just hide the 3D shape. And we will continue on this new gen shape here. Okay, and as you can see, it's a dead solid. Now I will just switch to the functional generative shape design. You can also have this exploration assistant that is actually really good. It will automatically create a simulation file because topology optimization is from SIMULIA application. Okay, you will create this new simulation file that will be on top of the part, meaning in terms of hierarchy. So you see, it's a simulation containing model, scenario, and result, and inside the model you have the shape, the part. Okay, so here it's very nice, this assistant, because it tells you more or less all the steps you have to do to get the optimization on your part. And what we can see here is we have to make a design space of this. And we see already that we will already remove that element here because we don't want the original part body. I will just remove that. And here later we will select this as a design space. But I'm going back to my bracket here now, and I will just, I'm in the body 2 here. I will just modify a bit that. So we make a design space, so basically a larger volume for the study. Okay. Yeah, well, can keep the link. I guess it's because that. Just in case, I'm going to delete that. Delete my sketch and do it again because I had a link with the 3D shape and I don't want that. Okay, I do it again. Quickly, let's put some space between my original shape and the new shape I have here. Actually, something like that would be nice because I already made a bit the part, so I know already a bit the shape, but I can tell you that this will be nice for the simulation. Don't do too big because the software will not give you a good result if it's really big design space. And of course, if I exit right now, the hole will be covered and we want to keep the hole. So I will just make quickly the hole. And I will show you again this very nice tool that we have now. We can say that they all have the same diameter just by clicking on the equal feature. Be careful here because I have a small small tangency here. So I click on the upper arrow, and I can just select the tangency here, saying that I want to delete it. And here we can put the diameter of 10. Yes, and this is not concentric here, so I will select the two circle, right click, concentricity, and same for this one. So you see I select this circle, the cylinder, I put a constraint, and I just right click on concentricity. Okay, so if you follow me now, we can just make a pad of that, and you put 5mm, just to show you, pose direction, mirror extended, yes. And that will be our design space. So you can see it's a big block, a big volume. Okay, now I can go back to my simulation, where we have this nice assistant here, and now we can say the design space. So we don't want the 3D shape here, so I just remove that. And here we want that as this one as the design space. Yes, here it is. Okay, and well, the next step is to add functional region. So functional region will be the region that will not be affected by the optimization. So we go back to this level here on the abstraction shape, and you go in design space, because that's what we're working on, and we have this partition feature. It asks you to make in another body, but in that case we already made the abstraction shape, so you can just click no, and it will make the partition directly in this body here. So with this feature, you can automatically detect the cylinder, and that's pretty cool. 5mm is actually the good dimension, so I click on OK, and you can, of course, I could have continued doing that. Oops, don't want that. You want this one and this one. Yes. So how is okay? I have two solid partitions, so I will just delete what I've done, edit this one instead, and just add my hole directly here. Okay, now we can select the functional regions in our design space, and we can select this one, and this one. Okay, it finds all the functional regions, so that's already good. And now you have a green tick saying that this step is already done. We can continue. Meshing setup, okay, just click on OK. You find automatically the right size. It's going to be tet mesh. You can select linear or quadratic. In that case, it's very simple. I'm going to keep linear and click on preview if you want to have an overview before. Okay, it's a pretty big design space, but it works fine for my tet mesh. Click on OK. If you want to, you can also have a quick overview on your mesh element. It's TE4 for tet mesh. Okay. Let's continue with analysis setup. You need to add loads and restraints. That's the minimum. Let's start by the restraint, because we know that what is fixed, this face is fixed. See, I put a clamp in this one and this one. So I have two clamp, meaning that these two holes will be fixed. And I will add some load, and I just select the surface. It's very intuitive, very easy to use. You have several types, pressure, force, etc. And since it's a hole, I will select bearing load. You have X, Y, Z. I put on Y, it's the vertical one. I will put minus 500 Newton, so that will be about 50 kilo for a bracket like that in aluminium. That should be more or less right. Click on OK, and we have to define, this is a very important step you have to do, is to create a load case. And you have to create a new load case here, saying basically that you will select the clamp and the bearing in that load case. You can even create more, and you could also put -1 if you want to do the bearing load in the other direction. So it's possible to twist a bit, make other load case, and have several simulation, of course. So I will just do simple one simulation is enough for today. We have analysis setup in green. I continue. setup validation. So click on validate setup. It will run the simulation just to test if this is okay already. So this might take some time, so I will probably forward it in the video. Well, it went pretty fast, even less than 30 seconds, so that was pretty nice. Here it gives you a very basic result for the beginning. Of course, you have some fix here, so it's normal that you have some constraints. But it gives you the von Mises traces. Okay, I will continue now with the topology optimization part, where I will select the optimization target. You have several ways. You can maximize the stiffness, maximize the frequencies, or directly minimize the math. And I will select maximize the stiffness because we still want this bracket to accept this 500 Newton. And I will say that I want 30% of the mass of this volume. 30, we can put 20, we can put, you can try different way. It's possible to reducible optimization to have different results. So I click on OK. Constraints here, you can add some constraints if you want to add center of gravity, if you want to add fastener in that in some hole. You can also do this stress constraint, but then you will double the time of the simulation. You can of course add displacement, etc. I will just skip this skip this step, and as you can see, it's a square, so it's a green square saying that it's just optional. Shape control, also here you can add some thickness control if you want that everything is 1 millimeter thickness, especially if you do that for molding. We can add some shape control such as draft or casting control if you have center a plane in the middle of the mold, and cyclic if it's cylindrical, etc. I will just add symmetry in that case just to show you that, of course, I have a plane here in the middle, so I can just select this plane here. I'll click on OK, and now it's already selected the symmetry as this one. So basically it will be the same result each way of the plane. And now it's time to run the compute shape. So here I do it on my local machine. 4 cores is the maximum I have, and the software is limited to that. So maximum number of iteration, 60 is the average number. Basically, if it's going over that, it will not converge. So it will not give you a result. 60, let's try how much we will get. Click on OK. Okay, so as you can see, it took about 8 minutes to do the results, and it took 34 iterations before getting the 30% mass. So we reached 29%, so it's pretty good, conserving the stiffness. And as you can see, that's the iteration curve. Okay, so here is what we can do next, is to compute the shape according to the iteration we got. So to generate the topology optimization. So you click on concept shape here, just under compute shape. And here you have this, let's say this panel that appears that propose you here to control a bit the results. So according to so that's more or less the ISO. And here you have directly the weight showing here. So it's pretty nice because we have a different overview of what we can normally have. So it's a nice way to show you design. And let's put a bit more, like 50 on the ISO. That should be pretty nice. We are at 30% of the residual volume, and we reach 200 kilogram. That's pretty nice. 200 gram, I mean, sorry. And then you have two types of smoothing. You can either do the simple one, that will give you this rough smoothing. I will just select this one, will give you a nice smoothing of the shape at the end. Generate concept shape, it takes some time to create the 3D model from that, but it goes pretty fast. Okay, here it is. As you can see, you have a nice smoothing for the shape. You can directly reuse that for 3D printing because it's pretty smooth. Of course, if you want to have even better results, you can create a freeform surface. So it will be basically based on imaginary shape functionality. And I will just quickly show you what you can do. Is from this feature, you can just make some shape directly on the 3D shape to generate a nice smooth surface on your 3D model. Okay, and if you are not satisfied with the result and you have here, for example, I can just after just move the point manually like I do here up in the second screen, and you can move the point manually also like in imaginary shape. Okay, so that was the way you do it with freeform if you want to rebuild, and now I want to show you how we can do it for automatic creation for manufacturing. So I will show you here. So I will just delete that, escape. No, I don't want. I will delete my subdivision surface. Okay. And we don't need the assistant anymore. Of course, you can continue, manage validation, create different version of this. As you can see here, I can select this new shape validation and we can make some simulation to run if it's working. So I can do it quickly. Here you validate that your part is okay. And here it is. Then you can see that your new part is also strong enough to get the 500 Newton. Okay, so what we can do now, I will go back to my bracket. What do we have here? Here we have the original part, as you can see, on the 3D shape. I will hide that. Now we have the new shape that is more or less optimized. We can either print it or we can mill it. And I will show you how we can mill this part. So you see you have different tabs, and here you have milling reconstruction. And what they ask you is just to select the shape. As you can see, it will make this block. Imagine that it's aluminium block. We can offset this to 1 millimeter. Okay, so then you see we don't touch already this. We have 1 millimeter offset. I click on OK, and we have this block of aluminium. And now I can just milling reconstruction. You select the concept shape, that is this one. We select the milling direction, is this one, along this plane. And we can select the size of the tool you have. So 10 millimeter, 5 millimeter, whatsoever. Preview. It will automatically detect all this contour of this part. Click on next, and then you have this nice panel that proposes you to select this this profile here and decide if you want accurate, medium, rough, and you can see there is some difference, or even spline. So if we select that, for example, rough, because it's not that important in that case. Same for this one, rough, and this one, rough. Then you have inside here, you would like to have accurate, but if it's a hole, it would be even better to select spline. Same for this one, spline. And oops, spline again. And if you want to, on the outer, you can select accurate. to have a nice profile, and just click on OK. And here it is. You see that your milling block has been milled. We still have 1 millimeter offset on the surface, so we can just do another time. And that way, the concept shape, you want the milling direction in that direction. Here, we can just preview the tool diameter can be 10 millimeter, even more. It's just going to mill the whole surface. Next. And yeah, accurate or spline even. Click on OK. And here it is. So now if we hide the concept shape, here is the part that is milled. Okay, so that was it for me today. I hope you understood how to work with functional generative design. It's very simple to use, and I think the best thing to understand is that we have the robustness of CATIA and the topology optimization from SIMULIA, and combined together they can really give you really great results, and you don't even need 3D printers for your part. You can even mill it, and at least that will give to designer a new way of thinking when they will design a new part. And I think that is great because the software is really here to help you achieving that goal. So thank you very much for watching this video. Do not hesitate to follow us on YouTube because we release a new video every Monday. And visit our website www.plmtechnology.com, and I hope to see you soon, very soon on our channel. Thank you very much. Goodbye.